last Thursday. So no questions. So okay. So first, I would like to give you a proof of a formula that we used, the so-called Feynman-Katz formula. So remember, I defined so you have your Markov chain on a space E, and you fix a function E. And you defined a functional P, which applied to a function F, gives you the expectation starting from x of the exponential 0t v xs ds, and then f xt. So you defined this functional by this formula, and what I claim is that this defines a semigroup, so in the sense that pt plus sv it's equal to ptv psv, and then that if you take the derivative of ptv, this is equal to L plus V PT V. Right, so we used this second formula when computing the expectation of the exponential. Okay, so let me first prove this, and then we go back to the proof of the hydrodynamical limit of the exclusion process. So let's prove the first identity. So I want to compute pt plus s v of a function f and show that this is pt v applied to ps v of f. But by definition, the left-hand side at x, it's equal to the expectation starting from x of the exponential, the integral from t plus s v x r dr, and here f xt plus s. All right, so what you do is you want to use the Markov property, so I will write this expectation as an expectation of the conditional expectation given ft. So I just write the same expression, taking the conditional expectation with respect to ft. So now we have a piece of this integral which is ft measurable, which is a piece from 0 to t. So this will get out from the conditional expectation. And then I have a second piece, which is the conditional expectation. And from this piece, you just apply the Markov property. So since you're conditioning at ft, and everything here depends of the process after time t. So what you do is that you consider that this is conditional expectation. It's you start your process from xt, and you look it at time, well, this time minus t, so that this conditional expectation by the Markov property is the expectation starting from xt of, so everything is shifted by t. So this integral becomes an integral from 0 to s, and f, it's xt, xs. And now, if you go back to the definition of your functional, you see that what appeared here, it's exactly the functional at time s and for the function f. So this is equal to p v s of f computed at the point xt. Right? This is exactly by definition. And so, if I call, so let me call the function g of x this function p, just to what we have here is that this is equal to the expectation of the exponential from 0 to t of vxr dr. And here, by definition, this is g of xt. And again, by definition, this is pt v of the function g computed at x. But the function g, it's, so we have pt v computed at the function p v s of f, and this is at x. So you see what we proved is that indeed, since this is true for all x, this function is equal to that function, which means that indeed we have proved that identity. Okay, so this equation defines a semigroup in the sense that pt plus s is equal to pt ps. So that's the first claim. So let's go to the second claim. Let's compute the time derivative. So to compute the time derivative, I want to compute dt v of f. So this is the limit as h tends to 0 of pt plus h but we have just seen that PTV is a semigroup. So I can write this as PH V PT VF minus PT VF H. So it's enough actually to compute this derivative at time 0. Okay? Because, well, I want to prove that this is equal to something PTV. So if I prove, so what I have to show is that the limit as h tends to 0 of pH minus PHF or G minus G divided by H, that this converge to L plus VG. Okay, so this is what. Okay, so you just replace this function PTV by G. So if we have this, then this is exactly what I claimed. Okay. So this is what I will prove. I want PVH of a function f minus f. Fine. So, and let me compute that at x. So let's go back to our definition, and let me call ht So t is small, it's converging to 0. And the computation we will perform, it's very similar to the computation in which we computed the derivative of the semigroup. So what did we do? We took the first time of the first jump. We considered two cases. Either this time happens before t or after t. And we have seen that it's not possible to have two jumps before t. Well, that the probability of this to happen, it's of the order t squared, so it doesn't matter. And we just repeat exactly the same argument here. So let me consider this expectation. And as I said, I will consider two cases. Either the first jump, which represented by tau1, happened after t, or it happened before t. So let's consider the case in which it happened after t. So if the first jump happened after t, this means that in the interval 0t, nothing happened, right? Which means that xs, it's constant equal to the initial position, and the same thing for xt. So in this case, what's written there, it's the exponential of t times vx, fx. And then I will consider the second case, right? Well, everything here is a constant. So this is exponential t vx, fx. And here we have the probability that tau1 is larger than t. We know that tau1 is an exponential random variable, which has parameter lambda of x. And so the probability that this exponential is larger than t, this is exponential minus lambda of x t. So this is this expectation. Let me take that minus fx, which is what's appearing over there, to get that this is f of x. And then let me divide this by 1 over t. So this is exponential t vx minus lambda x t minus 1 divided by t. And you see that this converges to fx. And here we have t times vx minus 1. So this is vx minus lambda x. Okay? So this is the limit of this term minus f. Right? So you see that we have already fx, vx, which is one of the terms. And now let's consider the case in which the first time it's smaller than t. So it remains to consider the case in which the first time it's smaller than t of right. And now I will use the strong Markov property. So I will condition with respect to tau1. We have seen that tau1 is Markov stopping time. It's a stopping time, so we can use the strong Markov property. And by taking the conditional expectation with respect to tau1, we have seen that this event is f tau1 measurable, so it gets out from the conditional expectation. here there is a piece, since tau 1 is smaller than t, there is a piece between 0 and tau 1, which also gets out from the conditional expectation. And so this is equal to the expectation of tau 1 being smaller than t, the exponential of 0 to tau 1 Vxs ds, and then the conditional expectation given f tau 1. Right? I'm just using the fact that Vx is f tau 1 measurable for tau less than tau 1. Fine. Now what can we do? Well, use here the strong Markov property to say that this conditional expectation, it's, well, you start at time 0 your process at the position x tau. And here what happens is that you have the exponential from 0 to t minus what I will call this tau star, or t star, of Vxs ds f x t minus t star. Okay, so you compute this. This is a function of t and t star, right? And then you replace t star by tau, which is this tau here, tau 1. Okay, so this computed at t star equal to tau 1. Okay. Otherwise, you can just write here tau 1 and understand that tau 1 is this variable which is fixed. Okay? So, what I have here on this second expectation, I will compute it. Just observe that here, since I'm integrating between time 0 and time tau 1, this v is constant. The trajectory is constant up to tau 1. It's equal to x. So I can replace this exponential by the exponential tau 1 v of x. Now, let's consider this. Mind that this is bounded, right? And here I already have an event which has probability t. Okay? Just observe that the expectation that you start from x so v t tau, it's bounded by t, so this expression, it's bounded, right? Here f, it's bounded, v, it's bounded, so this expression, it's also bounded. So everything here, it's bounded by a constant times this expectation. Okay? And this probability, it's the probability that I have an exponential random variable which is bounded by t. Okay? So this is the probability that an exponential of parameter lambda x is less or equal than t, right? And so this is 1 minus exponential minus lambda x t, and this is of order t. Okay. So this is giving me a term of order t. I will be dividing it by t. So in this expectation, anything which is also of order t can be neglected. In this expectation, I'm only interested in the terms of order 1. Right? Do you agree with that? Right? This is the fact that I'm integrating here over the set that tau1 is bounded by t gives me already an expression which is of order t. And since I'm dividing that by t, everything which is order t squared can be neglected, which means that here everything which is order t can be neglected. Right? So let me write what we have here. We have the expectation. So let me replace x tau by y. And in this expression, I can repeat exactly my argument and saying that, well, let's see that the first jump, it's less or equal than this value, t minus t star, of exponential plus all right? So I just decomposed this expectation in two pieces. And what I'm claiming is that this second piece, it's, sorry, the first piece, it's order t. Because the first piece, this expression, it's bounded by exponential t times vx. T is small, it's bounded by 1, so this is bounded by exponential the L infinity norm of v. This is bounded by the L infinity norm of v. It remains this probability, and as we have seen, this probability, it's of order t minus t star, so it's of order t. Okay? So this expression, it's order t. Since I have here another expression which gives me a further t, I can just neglect that. Okay, so this piece here will not contribute to the limit, while the second one, in which I'm conditioning that tau1 it's larger than t minus t star, I can repeat exactly the same argument. So if tau1 it's larger than t minus t star, this exponential it's equal to vy times t minus t star. Right? Because if the first jump happened after this time, this means that in this interval 0t minus t star, the process remained at y. So this is v of y times t minus t star at the exponential. Then f, it's f of y. Okay? And what remains is this probability. The probability that starting from y, tau1, it's less than t minus t star. Larger, sorry. And this probability, we know, it's exponential minus lambda of y, t minus t star. Okay? So what I proved is that this exponential, in conclusion, so that the exponential starting from y of exponential that this is order t plus the what I wrote there, which is exponential t and here exponential minus lambda y t minus t star. Okay? But now I can go further and say, well, this exponential, it's actually equal to 1 plus a term of order t minus t star. And the same for this one. Okay, so I have here f of y, 1 plus order t minus t star, which multiplies the same thing. So actually, this is equal to f of y plus a term of order t. You agree? So this is the contribution of this expectation. Okay, so we just computed this expectation with y as x of tau. So I can, this second expectation is actually equal to the expectation starting from x, the indicator that tau 1 is less than t, the expectation of tau 1 v of x, and we have seen that this second expectation is actually equal to f of x tau plus order of t. Right? You agree? So, where this order of t, it's an expression which is absolutely bounded by constants time t. Now recall that this expectation here, it's also order of t. So I will rewrite this expectation as a term which is of order t squared, which is this times this, plus what remains, which is the expectation starting from x of tau 1 less than t, and then exponential tau 1 v of x, f of xt, x tau. Okay? Now I could argue that tau 1 is less than t. So this is bounded by exponential t times something, and this is again 1 plus an order t. So I can replace that by 1. Okay? Because tau 1 is bounded by t, so this is 1 plus t. So I can replace this by 1. And what remains is that tau 1, it's an exponential random variable with parameter lambda of x, and x tau, it's the position after the jump, and we know that this has a distribution given by px. So this expectation can be written as an integral from 0 to t of lambda x exponential minus lambda of x of s. This is the time at which the process jumps, and it's bounded by t. So this is the probability that the tau 1 is equal to s. And now fxt is the sum over all y of p x y f of y. Right? So this does not depend on t, while this expression, if I divided it by 1 over t, it will converge to lambda x because, well, this is a continuous function in S, and at S equal to 0, it takes the value lambda x. So these converge when I divide it by t to lambda times r. So this is y different from x of r x y f of y. Right? So this is the contribution of the second expectation. So now, if you recall that the contribution of the first expectation, it's fx vx minus lambda x fx. You sum the two. So what we proved is that this is converging to this term, which is fx vx minus lambda x vx, and then plus that term. Okay, and I'm summing over y different from x because I'm waiting for the first jump. So at the first jump, well, it jumped somewhere, so it jumped not to the same side. Okay. And now if you remember that the sum of rxy in y gives you lambda, so you can put, here it's fx lambda x. So that's wrong. This is f. So you can put, you can rewrite this as fx vx plus the sum over y of rxy fy minus fx. And this is exactly what I claimed. So this is what I erased, but this is f of x vx plus L of fx. So it's indeed v plus L. Okay, so, well, this is the proof of the Feynman cat and completes the proof of the bound I gave you Thursday. Questions? Fine. So this was a parenthesis. Now we can go back to the proof of the hydrodynamic augment. So we were studying an exclusion slightly different, in which the generator, so in which you exchange, but the rate at which you exchange depends on your neighbors. So the model I proposed was this one, with rate 1 plus a times eta x minus e plus eta x plus 2e, you exchange. What happens at x and x plus e? Okay. And I told you, well, let's repeat exactly what we did for the symmetric exclusion process. So we define this process. We have the empirical measure. And this empirical measure and this dynamics, if you start your dynamics from a sequence of measure mu_n, where mu_n is associated to some density profile gamma, then this defines a measure, which I'm representing by Q or P, I don't remember. So a measure P, mu n, on the space D, 0T, M. And I want to show that this sequence of measure converge weakly to a measure P. So this is my goal. I want to show that this sequence is converging to the solution of some PD, some PD. So how you do that? We proceed in 2 steps. We prove uniqueness of the limiting point, and we proved that the sequence is relatively compact. It's tight. So to prove uniqueness, I propose to follow exactly the same strategy that we used for this symmetric exclusion. Take a test function. So let's take a test function g in C2 of t, the torus, and let's consider pi n. And remember here I'm taking at time n squared, so I'm speeding up the process by n squared. So I won't multiply t by n squared. I'll just assume that I'm multiplying the generator by n squared, which is the same thing. And let's define a martingale, which is taking, so here, mind, I'm multiplying the generator by L, by n squared. So let's consider this martingale. And let's call this martingale MT of G. And maybe N. So this is my martingale. Okay. So first, I will prove that this martingale is converging to 0. So I will show that this martingale MGNT square, it's converging to 0. So I'll repeat here the computation just to make sure that this piece is clear. Okay, and then by taking that this martingale converges to 0, what I get is that and I can even get here a supremum over T. So, okay. So let me write that precisely. So what we'll show is that the square of this martingale converges to 0. And that will imply by Doob inequality that the probability that the supremum for t less than t of m n g t less than epsilon, that this goes to 0 for all epsilon. Okay, so I'll conclude that this supremum goes to 0. And then, well, I have 2 pieces which are very nice because they are expressed in terms of the empirical measure, which is our object. But here we computed, and there is a piece which is not a function of the empirical measure, and this is what the Thursday lecture was about. It's to make this object a function of the empirical measure. So we from this plus the result of Thursday, which is a replacement lemma, we will conclude that P will conclude uniqueness. Okay, so this is the roadmap. First, you show that the martingale vanish. From the fact that the martingale vanish, you conclude that this probability vanish by doing inequality. Then you write down what this is. You get a sum, but here, unfortunately, this sum, this expression, it's not a function of the empirical measure. But then you can use the result I presented Thursday in order to turn it into a function of. And once you have a function of the empirical measure, it can just pass to the limit because you are assuming that you have a subsequence which converge. So you can get informations on P. And these information on P will tell you that any limit trajectory is actually a weak solution of some partial differential equation. And then by using uniqueness of weak solutions, you deduce that actually P is concentrated on the solution of the PD. Right? And this is exactly what we did for the exclusion process. Okay? So I'll go step by step. I'll first prove that indeed these martingale vanish. And then I will go to the second step and recall what we obtained, so the formula for this expression, and deduce from that the uniqueness. Is it clear what the strategy is? Okay, so maybe I'll leave this. I won't touch this blackboard, and let me first show that the martingale vanish. So I want to consider 1. And for 1, we have seen that this is the expectation of this martingale is actually equal to the time integral of gamma and SDS, where gamma is L of the function square minus 2FLF. Mind that here we are multiplying the generator by n squared. So there is an n squared in front. And f of eta is the function pi g. Okay, so this is our gamma. So let's compute this formula. Let's compute the formula for gamma. So gamma, it's equal to n squared. And what we proved, it's actually we can write gamma as n squared times the sum of x, the rate at which you exchange, and here f sigma x, x plus e, minus f of eta square. Okay, so this is what computation we did, right? So I just have to compute this expression. So let me write this as Cx x plus e of eta. So it's a certain function which is bounded. And now, here, what we are doing is that we take this integral And so you see that this computation, it's exactly the same one as for the symmetric exclusion process. Okay, you integrate a function g, which is C2, with respect to the empirical measure, you change x and x plus e, and you compare with the original. So no difference between this computation for this model or for the symmetric exclusion. The difference appears in these functions, in these rates. And here, if you remember, what we obtain is that this is equal to x plus e minus eta x times g x plus e minus g of x square. Right? If you don't recall, just go back to your notes. You'll see that this is exactly what we computed. This is what we obtained. Now, well, I can bound. So I have n squared. This rate, it's bounded by a constant. Eta x plus e minus eta x squared, it's also bounded by a constant. So what remains, it's gx plus e minus gx. And sorry, there is 1 over n here, which I'm forgetting, which comes from the 1 over n of the sum. So I forgot that n, which is very important. So this is bounded by a constant. So what remains? I have 1 over n, and this difference, since g is C2, it's bounded by a constant divided by n. Okay, so this expression, it's bounded by a constant divided by n squared. And I'm taking square, so it's bounded by a constant divided by n to the 4th. Now I have a sum of n terms. This is multiplied by n squared. It's n cubed divided by n fourth. This is of order 1 over n. And this tends to 0. So this martingale indeed tends to 0, and therefore by dupe I have that this probability is converging to 0. Right? So this is the first step. Now I can go to the second one, which is writing down this martingale. So actually, what we are interested in is that n squared times L by n g. Right, so this is this term here. And, okay, that you'll need to help me or to get the exact expression, but our computation gave us 1 over n, the eta x, the discrete Laplacian of g. Okay, so this was the contribution of the 1 in our rate. Okay, so if we and then I had a divided by n, maybe times a constant, which I don't remember, and times a function which was eta x plus e, maybe eta x minus e, something like that, times g second of x. And a second expression, so maybe let me write this as a constant 1 plus a constant 2, and a function of the type eta x plus 2e of g prime of x. Okay, the difference between these expressions is that here we had one local function eta x, and it's translated by e, so eta x plus e, and the other one was translated by 2. but I don't remember the constant C1, C2 we had. And maybe here, instead of eta x plus 2e, I had eta x minus 2e, or eta x plus e, eta x minus e. Well, if you have the exact formula, you tell me. So C1, how much is C1? 1, fine. And here, do I have eta x plus e? Minus e. Okay. And here? Sorry? And that's correct. Okay. So this is what we obtain. Okay. So I have that this expression, if I take the supremum, it's converging to 0. Okay? This one, it's very nice because I can replace these discrete Laplacian by the continuous Laplacian, paying a cost 1 over n, but that's fine. And so this one I can write as pi n g second. But this one I'm not able to write as a function of the empirical measure. But now, let's recall what we proved. And this was the main result. So the theorem was that if you take the expectation of an integral from 0 to t of 1 over n x, nice function h of x, and then eta x plus e or plus 2e, that's not very important, that this minus 1 over 2 epsilon n y minus x less than epsilon eta y square, this is time s, so that if you take the difference of this function with that function, you integrate that over t, and if you take the limit sup as n tends to infinity, and then the limit as epsilon goes to 0, that this is equal to 0. For all t and for all h. H, voila, you need some regularity. Say h continuous. Right? So this is what we proved. So let's go back to this martingale. Well, if you have objections regarding that, let me know. So let's go back to the martingale. We have here the integral of this expression. We computed this expression. We have one which is fine, but the other two are not functions. But now we can apply these theorem and say, well, here I have a continuous function, so mind that I have an integral in this expression. So these expressions are integrated in time, so let me integrate them in time, 0t ds. So let's forget about the first one, but let's here add So this is what appears. And now I can say, well, I can replace this expression by that one, by the square. And this will be small. So let me rewrite, add and subtract this expression. Add and subtract. Okay. So the difference will converge to 0 if I send n to infinity and then epsilon to 0. So let me call the difference a remainder which depends on n and epsilon. And so okay, so this expression will tend to 0 in expectation as I send n to infinity and then epsilon to 0. And I'll do here the same thing. Okay, so let's forget this third term because I just repeat exactly the same thing. Let's focus on the second. So the second term, it's equal to an time integral g second of x, and then I have 2 epsilon n plus r epsilon n. Okay. So this is the second term. And mind that the third term will be exactly the same. Okay, so actually I can consider them together. Okay, here I subtract and add this term. The difference, it's small, and I keep the square. But the square is just that the difference will be that instead of this function, I have that function. Okay, so but both will be replaced by the square. So actually, I can write the sum of the second line plus the third line as this, just by adding a 2. To agree, I do exactly the same thing I'm doing for the second line to the third line. So the third line, I'm adding and subtracting this expression to this term. The difference, by my theorem, it's a remainder which goes to 0, and what remains, it's exactly equal to the 1, because I have g second on both, and I have a on both. So I just have 2a. So this is the contribution of the second and third line. Okay? And now here is the point, is that this is actually a function of the empirical measure. Okay? Because if I take a function the indicator of x minus epsilon, x plus epsilon, and I integrated that with respect to pi n. Well, it's the other way around, but let's write it in this way. So what is this? This is the sum on y of eta y chi x minus epsilon x plus, and I divide that by 2 epsilon. To epsilon at y. So this is equal to 1 over 2 epsilon n sum over y of eta y times this indicator, but this indicator is telling me that I'm summing over all y which are at distance less than epsilon from x. So this is y minus x less than epsilon. And this is exactly what's written here. Okay, there is a difference between 2 epsilon n plus 1 and 2 epsilon n, but that you don't care. Okay? You don't care because you divide it by 2 epsilon n, you multiply the ratio between 2 epsilon n plus 1, it's of order 1 over n. Epsilon n, but n is tending to infinity. So actually, this is equal to 2 times a, the integral from 0 to t, 1 over n, x, g prime x, and here I have pi n, which is integrating 1 over 2 epsilon, pi n, which is integrating x minus epsilon, x plus epsilon square. And this is at time s ds. And plus r epsilon n. Right? So that's fine because now let's go back to this formula. I have this supremum m n g t. I wrote it as pi nt g minus pi n0 g minus minus 2 terms, 0t pi ns g second plus 2a g second of pi ns chi x minus epsilon x plus epsilon square, and then plus an epsilon n. Okay, so this is the martingale. And so I want now to use this and this so that the Rn is going to 0 in order to get an information on this expression. So I'll say that the probability mu n that the supremum of tau less or equal than tau. So let's call this expression the sum as h of pi, because it's a function of pi. Right? Supreme that h of pi and t, it's larger than epsilon. If this is larger than epsilon, either the martingale or the remainder, it's larger than epsilon over 2. Okay, I'm writing the martingale as this expression, big expression, which is, I'm calling h, plus the remainder. So if this h, it's larger than epsilon, this means that either the martingale or the remainder, it's bounded, it's larger than epsilon over 2. So this is bounded by p mi n or epsilon n. But this one we proved that it converges in L1 to 0. So you can use Chebyshev inequality to turn that into the expectation of R epsilon n. Then you know that this goes to 0 as n tends to infinity, and then epsilon tends to 0. And this one goes to infinity. Sorry, I'm using the same epsilon, many places. So let's put delta here. Okay, so I know that this one goes to 0 as n tends to infinity, and then epsilon goes to 0. And this one goes to 0 as n tends to infinity. So from that, I'm concluding that this one goes to 0 as n goes to infinity, and then epsilon goes to 0. So the conclusion is that if I take the limit as epsilon goes to 0, and then the limit sup as n tends to infinity of the probability mu n that the sup of t less or equal than t of pi n t g minus pi n 0 g minus the integral 0 to t of that expression, which I won't write it here, that this is bounded by delta, that this is equal to 0. Okay, so this is what we conclude. This is what we concluded from this inequality. Okay, this one is 0, this one is converging to 0. So this is what we conclude. And now I can start to prove uniqueness. Let's say that P, it's a limiting point, because now I'm happy because I can pass to the limit, because everything is expressed in terms of the empirical measure. Okay, so all my H, it's a function of the empirical measure. And so I can pass to the limit. So this means that, let's say that P, it's a limiting point of this sequence. So there exists a subsequence, nk, which is converging to P. And now let's consider only this subsequence. Okay. And since I know that for the sequence this happens, for the subsequence it also happens. Now I claim that this set here, it's a closed set. In the topology of D, in the Skoroha topology. This no difference between this claim in this context and the one for the simple exclusion process. Just that here the function changed a bit. Okay? You have here an expression, but since we are taking the weak topology and we are taking time integral, it's not difficult to show that this function is continuous as a function of the empirical measure, and therefore that you get that this function is continuous, and therefore that the set is closed. And the set is closed. But it's 0, so maybe I want it to be open. Yeah, so let me transform it open. If this is 0 for all delta, I can also take it larger than delta, and it's still true, and now I get an open set. Okay, and what I know is that if I have a sequence Pn converging weakly to P, and if O is an open set, then P of O it's less or equal than the limit imp of Pn of O. Okay? So let me transform that into an open set. Now with the strict inequality, it's an open set. It's converging to 0. I'm assuming that P mu nk is converging weakly to P. Therefore, by this inequality, what I get is that the limit as epsilon goes to 0 of P of the supremum for t less than t pi t g minus pi 0 g minus the integral from 0 to t ds. And so you see that here the sums are transformed into Riemannian integrals. So this is the integral over the torus of g second of x. And here I have the integral of pi at time s chi x minus epsilon x plus epsilon divided by 2 epsilon dx, and I have a 2, this is a square, and I have a 2a, and there is another term which is minus 0t ds g prime of x whole pi s dx. Okay, so this is what I get. So any limiting point P of my sequence P mu n will satisfy, okay, I did not write, this inequality. Do you agree with that? I just have these terms which are transformed into these. Okay? Questions? So this is what we get. So any limit point, it's such that this happens. Since there is at most one particle per site, we know also that P, the measure P, it's concentrated on trajectories P pi s dx, which are absolutely continuous with respect to the Lebesgue measure. Okay? So I can replace here this pi by this density, these integrals by Lebesgue integrals. So this will become u sx dx. And so let me write it. This one so let's see what we have over there. 0t ds I have a 2a. Then the integral over t dx, g second x, and then a square. And this square, it's the integral in t of u sy chi x minus epsilon x plus epsilon divided by 2 epsilon y dy square dx. So this is this term. This one, it's already in final form, so I won't touch it. I just want to consider this one, which depends on epsilon. I want to see its limit in epsilon. So this is actually 1 over 2 epsilon from the integral from x minus epsilon to x plus epsilon of u s y. And this is squared. And u, it's bounded by 0 and 1. It's a bounded function. So what's appearing here is that you're considering u, and you're modifying u with respect to a function which is an approximation of the identity, which is equal to 1 over epsilon, or 2 epsilon, between minus epsilon and plus epsilon. So you're taking a function u, you take its convolution with respect to this approximation of the identity, and you get this object. Okay? And so this is essentially, you essentially no, it's exactly taking convolution of u with respect to a kernel. Here the kernel is not very smooth, but we could have, in our proof, instead of taking this kernel, taking something smoother. But in any case, what we know is that if you take any bounded function, any L1 function, and you take its convolution with respect to a kernel, and if you compare this function with this function, so I'm comparing my function with the smooth, its convolution with respect to this kernel. And what I claim is that this object here, it's converging to 0 in L1. Why is that so? Well, this is true for continuous functions. Okay? If u is continuous, that's easy to prove. Now, if you take an L1 function, you can approximate it by a continuous function, and then you get this result. Okay? You fix some delta, then you have u. You approximate this u by a continuous function. The same one will be approximating this one, and therefore you'll pay a delta in order to replace this one by a continuous, this one by a continuous. But now you have a continuous function. This means that when epsilon goes to 0, you're in business. Okay? So this is true for any L1 function. This means that as epsilon is converging to 0, this expression is converging to that one in L1. And so I can send epsilon. So this means that I can replace, so this expression, which is integrated, will converge to the same one in which, as epsilon goes to 0, if I take the limit, this integral will converge to the same one where here I have u as x. So if I send epsilon to 0, then this expression will converge to 2a 0 t ds, the integral dx, g second of x, and here I'll get u as x squared. Right? So if I send here the limit, I can repeat my argument. This expression is converging to that one. So if I take here an open set, I can again deduce that if P is a limit point of this sequence, then what I have is that the probability of the supremum of utx minus u0x gx minus the integral from 0 to t ds, the integral from on the torus dx. Then we have g second x u s x plus g second x 2a u s x squared. That this is larger than delta, that this is equal to 0. And since this is, and this holds for any g in C2. And since this holds for any g, okay, so this, you know that this is true for all delta, you send delta to 0, and you conclude that your measure P is concentrated on configurations for which this is equal to 0 for all t. And this is telling you that U, it's a weak solution so you integrate by parts twice to get that utx minus u0x, it's equal formally to the integral from 0 to t of the second derivative of u plus 2a, the second derivative of u squared. So formally, what you get is that u is the solution of dtu, it's equal to the second derivative of u plus 2a u squared. Or in another, writing this in another form, this is dx of 1 plus 2au dxu. So now you get a nonlinear partial differential equation, right? And with the initial condition, which is given by this the u0 that you get from the initial measure. Okay, we started from an initial measure which had a density profile, and this will give you the initial condition. Of course, you have to prove that, if you prove that this equation has a unique weak solution, okay, so that there exists a unique u which solves this equation, okay, that for all g and all t this is 0. If there exists a unique u, you just proved that any limit point, it's concentrated on these trajectories. Okay? So the proof, it's exactly the same one as the proof of the exclusion, but we had this further step that we needed, this replacement lemma to close the equation, to express the martingale in terms of the empirical measure. But otherwise, the strategy of the proof for this model is exactly the same as the one for the symmetric exclusion process. And again, well, it's based on the uniqueness of weak solutions, and sometimes you are forced to prove that your solution U has further properties. So maybe it's not enough just to show that it's a weak solution. You don't have a uniqueness of weak solutions, but you need further properties. So you need these functions to have finite energy, which means that you need to show that these functions have a gradient, a generalized derivative, which is in L2. So you need to prove that actually P is concentrated on trajectories U, which have a generalized derivative which belongs to L2. Okay, so that's common in these, in the field of weak solutions. It's a common condition to impose, which can be proved for these models. Okay, so maybe if I have time at the end of this lecture, I'll show you how to prove that you are concentrated on trajectories with finite energy. So any question about uniqueness? You have a question? Yes.
So we got a polynomial of degree 2 because we were considering a window of size 2.
Yes.
When we were looking at the derivative, right? So if I want to get the polynomials of degree 3, I look at the window of size 3, or do I need to take problems of equals?
Yeah, you'll take, no, you'll take, okay, so if you do, let's say 1 plus A eta x minus 2 epsilon. Okay, so that's a nice computation to do. You should do it eta x plus 2 epsilon. Okay, you still get of order 2. So 1, you'll get equations of order 2. But you should be very careful by choosing these points in order to be able to perform a second integration by parts. So what I'm saying is that if you take minus 2 epsilon and plus 2 epsilon, you won't be able to perform this. I think that you'll need to go to put x minus 2 epsilon and x plus 3 epsilon here. Then with this very precise choice, you'll be able to perform this second integration by parts. Otherwise, you get what I called, or what's called, a non-gradient dynamics.
I was asking also about if I want to see on the...
Yeah, so that's the first point. So first point is you have really carefully choose these points.
And how do you know how to choose?
Just by computing.
Okay, so it's a guess.
Yeah, once you get used, you know more or less what you do. But yes. So you put here x minus 2 epsilon. You see, well, what's the point here I need to put in order to close the equations? Yes. And now if you want to go to, let's say, P, you have to take x minus epsilon, x minus 2 epsilon, x minus p epsilon. And if you do that, you'll get an equation of the order p plus 1. Or p, it depends on what you, well, here you get a polynomial of order p. But again, if you add this one, you need to add many other ones in order to close the equation. And it won't be this one plus another one. No, you'll have to, so you'll have to add eta x minus p minus 1 epsilon up to eta x minus epsilon, eta x plus 2 epsilon. and so translate these things from minus p to plus p, one step by one step, avoiding 0 and 1. I guess that this is the correct thing to get an equation.
And the reason why you're taking just products to get the polynomial to be equals 1, you take the products of p terms.
P terms.
The other eta that you need to get the degree comes from the I and M, right?
Comes from?
The action of the generator is pi.
Yeah, because this will give you an extra eta x, yeah. Any other question? Okay, but this is a nice computation to do in order just to realize that you need really a very special choice in order to be able to perform these two integration by parts, and therefore that most models are non-gradient. Okay, so this is uniqueness. And tightness, it's very similar, actually. So let me just recall how you prove tightness. So here again, you have to recall this Aldous criterion. And for that, as I claimed for the exclusion, you just need to prove that if you take a smooth function g, then this object here is tight, because we have seen that the space of measures is metrizable, so there is a distance, and in the way in which we construct the distance, if you are able to prove that these sequences are tight, then it's fine. So what we need to prove for tightness is that by Aldous criterion, you need to estimate pi n tau plus a g minus pi n tau g. For stopping times tau, which are bounded by t. And here, a, it's bounded by epsilon, and you're sending n to infinity, and then epsilon to 0. Okay, so we need to estimate this in supremum of all stopping times bounded by t, and supremum over all a bounded by epsilon. And then you send n to infinity, and delta epsilon to 0, and you have to prove that this is converging to 0 for all delta positive. Okay? So this is exactly what we did for the exclusion. And as for the exclusion, you write this difference as the martingale minus so you express this difference as a difference of martingale minus the integral term. Okay? But here, because we are able to do the second integration by parts, this term here becomes some constant times the second derivative of g times a function cx x plus e of eta, okay, which is bounded. Okay? So exactly as we did for the exclusion, you see, well, there is a 1 over n. You see that this term is bounded, and therefore this integral is bounded by a, and since a is bounded by epsilon, this one it's easy. And this one, then you can use Dubin inequality to say that this probability you use Doob inequality to say that this probability is bounded by, or Chebyshev inequality at this point, m tau plus a g minus m tau g square, and that this is equal to the expectation from tau to tau plus a of our gamma s ds. But the gamma we have seen is bounded by constant divided by n. And therefore, this is bounded by constant divided by n times a. And therefore, this goes to 0 as n tends to infinity. Okay, so this piece, it's as simple as in the case of the exclusion process. This proves tightness of the sequence, and therefore this completes the proof of the hydrodynamical limit. Okay? Fine. So let's stop here. And so maybe tomorrow, so we have essentially 5 lectures, I'll start with large deviations. Okay? So maybe I'll explain large deviations. Okay, so see you tomorrow.